Along a guarded river at night, the water remains largely undisturbed. No engine note carries across the surface, no rhythmic splash marks a crossing. Border sentries register only the absence of expected sounds, an unease that does not yet justify action. By the time certainty forms, the river has already returned to stillness. River boundaries imposed a particular kind of constraint on clandestine movement during the Second World War. Unlike coastlines or open terrain, rivers combined visibility, sound transmission, and predictable crossing points into a single problem set. Records suggest that in occupied regions, border guards relied less on constant patrols and more on the natural properties of water itself. Sound travelled efficiently across still surfaces. Disturbances were visible even at night. Any mechanical intrusion tended to announce itself well before it could be concealed. The operational requirement was straightforward in description, but difficult in execution. Personnel, equipment, or messages needed to cross narrow but controlled waterways without alerting sentries positioned along banks, bridges, or downstream observation posts. Documentation implies that this requirement arose repeatedly in river-dense regions where bridges were guarded, ferries were monitored, and fords were mapped and watched. The problem was not speed alone, nor capacity, but detectability. Conventional solutions failed to resolve this tension. Swimming was physically demanding, limited payload, and left evidence. Inflatable craft offered buoyancy but introduced a new problem: propulsion. Paddles and oars, while silent in theory, produced rhythmic surface disturbances and were difficult to use effectively against current. Period testing indicates that even skilled operators struggled to maintain direction without repeated corrective strokes, each one increasing the chance of detection. Small outboard engines existed, but their suitability was limited. Internal combustion engines of the period were noisy, vibratory, and mechanically exposed. Even at low throttle, exhaust pulses and metallic resonance carried across water. Attempts to muffle sound through simple shrouds or reduced revolutions tended to compromise reliability. Engines stalled, fouled, or failed to restart, leaving operators stranded midstream. Documentation implies that such failures were considered unacceptable in covert operations, where recovery was unlikely. There were also visual constraints. Metal hulls reflected light and produced wakes. Wooden boats absorbed water and required maintenance that could not be concealed easily. Inflatable craft reduced visual signature, but were structurally vulnerable. Sharp debris, submerged obstacles, or even prolonged friction against stone embankments could compromise integrity. The addition of rigid mechanical components increased this risk, concentrating stress at mounting points. Noise discipline extended beyond the engine itself. Guards were trained to listen for irregularities, splashes inconsistent with wildlife, mechanical rhythms, or the absence of expected ambient sounds. In some regions, it appears that stillness itself was monitored. A sudden silence, waterfowl disturbed, insects quieted, could prompt investigation. Thus, any crossing method had to account not only for sound production but for sound disruption. Existing mechanical solutions were ill-suited to this environment. Diesel engines, though efficient, were heavier and louder at idle. Petrol engines could be smaller but required higher revolutions. Electric propulsion was in its infancy and constrained by battery weight and limited endurance. Documentation from the period suggests that while electric motors were considered in abstract, their practical application in field conditions was minimal due to charging requirements and reliability concerns. Human-powered alternatives were equally constrained. Poling required shallow water and produced audible contact with riverbeds. Towing lines depended on fixed anchor points and exposed operators on the bank. Improvised cable systems were slow to deploy and difficult to conceal afterward. Each method solved one problem while exacerbating another. The psychological dimension compounded the technical one. Operators tasked with crossings reported heightened stress associated with prolonged exposure on open water. The longer a crossing took, the greater the perceived risk. This pressure incentivized speed, which in turn increased noise and visibility. Period accounts indicate that hurried crossings were more likely to fail, either through detection or mechanical mishap. Environmental variability further complicated matters. Rivers changed with weather and season, currents intensified after rain, water levels rose and fell, altering bank profiles and obstacle locations. A solution effective in one location might fail entirely in another. Documentation implies that planners sought adaptable systems rather than fixed designs, but adaptability often conflicted with simplicity and reliability. Attempts to disguise noise through timing, crossing during storms or at moments of ambient disturbance, were unreliable. Weather could not be controlled, and guards adjusted their alertness accordingly. In some cases, heightened conditions increased vigilance rather than reduced it. Reliance on chance was not considered a robust strategy. By the early years of the war, it was apparent that the problem was not merely one of quieter engines or better boats. It was a systems problem involving materials, mechanics, human operation, and enemy perception. Existing methods addressed components in isolation, but failed to integrate them into a coherent solution. Documentation implies growing recognition that a fundamentally different approach would be required, one that reconsidered the relationship between propulsion, structure, and sound transmission. At this stage, however, no such solution had yet emerged. The problem remained unresolved, and crossings continued to rely on compromise methods, each carrying its own risks. The pressure to move men and material across guarded rivers persisted, but the means to do so without alerting border guards had not been satisfactorily developed. As the limitations of existing river crossing methods became clearer, responsibility for addressing the problem shifted from field improvisation to centralized planning. Records suggest that by the middle years of the war, several clandestine organizations began to catalogue failures systematically rather than treating them as isolated incidents. This shift marked a change in approach. The problem was no longer framed as operator error or poor conditions, but as a technical mismatch between available equipment and operational requirements. Documentation implies that planners with experience in sabotage, courier movement, and liaison work were among the first to formalize the issue. These individuals were not engineers by training, but they were accustomed to translating field reports into practical constraints. Their memoranda emphasized recurring themes: excessive noise at low engine speeds, unreliable mounting systems on inflatable hulls, and the tendency for mechanical components to transmit vibration directly into the water. Engineers were consulted only after these patterns had been identified. Period correspondence suggests that early discussions were exploratory rather than directive. There was no clear specification for a solution, only a list of problems that any future system would have to avoid. This absence of a defined endpoint would shape much of the early work, leading to a series of partial concepts and abandoned trials. One early avenue involved modifying existing small engines rather than creating new ones. Records indicate that efforts were made to isolate engines from hulls using rubber bushings or suspended frames. In controlled testing, these measures reduced certain high-frequency vibrations but introduced instability. Engines shifted under load, misaligned drive shafts, and in some cases tore free from their mounts. Documentation implies that the unpredictable behavior of flexible supports outweighed any acoustic benefit. Another line of inquiry focused on exhaust management. Engineers experimented with extended exhaust paths, routing gases through water or through layered baffles. Period testing suggests that while these modifications reduced sharp exhaust noise, they increased back pressure and reduced engine efficiency. Engines overheated or lost power, particularly when operated continuously at low speed. In at least one recorded instance, an engine stalled mid-test and could not be restarted without removing the exhaust modification entirely. Attention then turned to the interface between propulsion and water. Early concepts explored alternative propeller shapes or shrouded propellers designed to minimize cavitation. Documentation implies that these designs were inspired by marine research rather than covert operations. In practice, they proved sensitive to debris and weeds, which were common in river environments. Entanglement not only reduced propulsion but created additional noise as operators attempted to clear the obstruction. Some planners proposed abandoning rotary propulsion altogether. Concepts involving reciprocating paddles or oscillating fins were discussed in theoretical terms. Period notes suggest skepticism from both engineers and operators. These mechanisms were mechanically complex, difficult to seal against water ingress, and prone to wear. No evidence survives of full-scale prototypes being tested, indicating that these ideas may not have progressed beyond preliminary sketches. Material considerations also entered the discussion. Inflatable boats were typically constructed from layered fabrics coated with rubberized compounds. Engineers questioned whether these materials could serve a dual purpose: structural integrity and acoustic damping. Early experiments involved attaching rigid components directly to reinforced sections of the hull. Documentation suggests that while this reduced the need for separate mounts, it concentrated stress and led to premature material fatigue. Human factors were not ignored. Operators were consulted about handling characteristics, maintenance demands, and failure modes. Their feedback often conflicted with engineering priorities. For example, a configuration that minimized vibration might require precise alignment or frequent adjustment, tasks that were impractical under field conditions. Records indicate that several promising concepts were discarded after operator trials revealed unacceptable complexity. Throughout this phase, the absence of a clear organizational owner slowed progress. Multiple departments expressed interest, but none assumed full responsibility. Engineering teams worked in isolation, addressing individual problems without integrating their solutions. Documentation implies that this fragmentation led to repeated rediscovery of the same limitations, as lessons learned in one trial were not always communicated to others. There were also institutional constraints. Resources were limited, and priority was often given to weapons or equipment with more immediate impact. A quiet river crossing system was seen as a niche requirement, important but not decisive. As a result, early projects were underfunded and subject to interruption. Test programs were delayed, and prototypes were dismantled to reclaim materials. By the end of this exploratory period, it was apparent that incremental modification of existing systems would not suffice. The accumulation of partial failures suggested that the problem required a more integrated approach, one that considered propulsion, mounting, materials, and acoustics as a single system. However, at this stage, no consensus existed on how to achieve such integration. What emerged instead was a growing body of negative knowledge, a clearer understanding of what did not work. Engineers and planners began to recognize that silence could not be achieved by suppressing noise alone. It required preventing noise generation at its source and limiting its transmission through every interface. This realization would shape subsequent efforts, but the means to implement it had not yet been defined. As discussions continued and priorities shifted, the groundwork was laid for a more focused development effort. The problem had been articulated, the failures documented, and the limitations acknowledged. What remained was to translate these insights into a coherent design philosophy, something that had not yet occurred. The transition from exploratory failure to a defined design effort appears to have occurred quietly, without a single directive marking the change. Documentation implies that once enough negative results had accumulated, a smaller group of engineers was tasked with reconsidering the problem from first principles. Rather than asking how to quiet an engine, they reframed the question: how could propulsion be achieved while minimizing the generation and transmission of detectable energy into the surrounding environment? This reframing altered the technical priorities. Noise was no longer treated as an output to be muffled, but as a byproduct to be avoided. Vibration, resonance, and wake formation were examined as interconnected phenomena rather than separate issues. Period notes suggest that this systems-oriented approach distinguished the later design work from earlier attempts. Central to the new concept was the relationship between the propulsion unit and the craft itself. Previous designs treated the engine as a rigid object mounted onto a flexible hull. The revised thinking inverted this relationship. Instead of isolating the engine from the boat's material properties would be used as part of the isolation system. Rubberized fabric, previously viewed as a structural compromise, was reconsidered as an acoustic asset. Engine selection followed this logic. Rather than adapting a standard outboard engine, engineers sought a power unit whose operating characteristics aligned with the constraints. Period testing indicates a preference for low-revolution operation, even at the cost of reduced peak power. Documentation implies that smaller displacement engines, when tuned for steady torque rather than speed, produced fewer high-frequency vibrations. These vibrations were known to transmit efficiently through water and were therefore prioritized for reduction. The engine casing itself became a design variable. Instead of exposed metal housings, the unit was enclosed within a layered shell incorporating rubberized compounds similar to those used in the boat's construction. This enclosure served multiple purposes. It dampened mechanical noise, reduced resonance, and protected the engine from water ingress. Records suggest that sealing was a persistent challenge, as excessive enclosure risked overheating. The final balance between insulation and ventilation appears to have been achieved through trial rather than calculation. Propulsion transfer posed another constraint. Conventional propeller shafts required rigid alignment, which conflicted with the flexible mounting concept. Engineers explored short, direct drive configurations that minimized shaft length and reduced the number of mechanical interfaces. Documentation implies that flexible couplings were used selectively, not to allow movement, but to absorb residual vibration before it reached the propeller. The propeller itself was redesigned with detectability in mind. Period testing suggests that blade shape and rotation speed were optimized to reduce cavitation rather than maximize thrust. Cavitation bubbles, even when small, produce distinctive acoustic signatures. By operating at lower speeds with broader blades, engineers aimed to move water rather than cut through it. This choice reduced efficiency, but aligned with the operational requirement for short, controlled crossings. Mounting the propulsion unit to the inflatable hull required further compromise. Rigid transoms were avoided. Instead, reinforced sections of the hull were integrated during manufacture, distributing load across a wider area. Documentation implies that this approach reduced stress concentrations and allowed the hull material to act as a vibration absorber. The engine was not bolted in the traditional sense, but secured through layered attachments that combined mechanical restraint with elastic compliance. Control systems were simplified deliberately. Throttle response was damped to prevent sudden changes in engine speed, which were known to produce audible transients. Steering relied on subtle adjustments rather than sharp turns, minimizing wake disturbance. Period notes suggest that operators initially found this sluggish, but adapted with training. Fuel and exhaust management were treated conservatively. Rather than complex exhaust routing, the design emphasized steady combustion and minimal exhaust volume. Exhaust outlets were positioned to avoid direct interaction with the water surface, reducing bubbling noise. Documentation implies that this choice limited engine output further, but contributed to overall acoustic reduction. Testing of the integrated system appears to have been incremental. Engineers evaluated not only sound levels but operator workload, reliability, and recovery from minor faults. Records suggest that while the system was not silent in absolute terms, its acoustic signature blended more readily with ambient river noise. Importantly, the absence of sharp or rhythmic sounds reduced the likelihood of human detection. Despite these advances, the design was not considered universally applicable. Its effectiveness depended on specific conditions, short crossings, controlled loads, and trained operators. Engineers acknowledged these limitations in internal reports, noting that the system traded versatility for discretion. At this stage, the focus remained firmly on technical performance. No consideration was yet given to large-scale deployment or operational doctrine. The design existed as a solution to a narrowly defined problem, validated through controlled trials but not yet tested against an alert adversary. The next challenge would be to move this system from experimental context into real-world use, where variables could not be controlled and enemy responses would shape its value in practice. The movement from controlled testing to operational use introduced variables that no design process could fully anticipate. Documentation suggests that initial deployments were deliberately limited in scope. The system was not issued broadly, nor was it treated as a standard piece of equipment. Instead, it appears to have been assigned to specific tasks where river crossings were unavoidable, and alternative methods had already failed or been deemed too risky. Operational use exposed the design to environmental conditions that differed markedly from test environments. Rivers selected for crossings were rarely uniform. Currents shifted unpredictably near bends, submerged obstacles altered flow patterns, and banks varied in composition. Period reports indicate that operators were instructed to conduct reconnaissance, not only of guard positions but of water behavior itself. The system's reduced power margin meant that misjudging current strength could result in slow progress or lateral drift. Despite these challenges, early operational feedback suggests that the system achieved its primary objective, reducing detection during crossings. Guards accustomed to listening for engine noise or rhythmic paddling reported fewer disturbances. In some cases, crossings occurred within audible range of sentry posts without triggering alarms. Documentation implies that the absence of a clear acoustic cue created uncertainty rather than immediate response, delaying any reaction until visual confirmation was obtained. This delay was significant. Border guards were trained to respond to anomalies, but not all anomalies prompted immediate action. A faint, irregular sound that did not match known signatures could be dismissed as environmental noise. Period accounts suggest that this ambiguity worked in favour of the operators. By the time suspicion arose, the crossing was often already complete. However, the system's limitations became apparent as use expanded. Reduced speed increased exposure time on the water. In regions where guards employed searchlights or flares, prolonged crossings heightened risk. Documentation indicates that operators adapted by selecting narrower crossing points, even if currents were stronger, accepting increased handling difficulty in exchange for reduced exposure duration. Enemy reactions evolved gradually. There is evidence that some border units adjusted their listening practices, focusing less on engine noise and more on visual disturbances. Wake patterns, however subtle, became a point of attention. In response, operators modified their approach, reducing speed further near banks and timing landings to coincide with ambient disturbances such as wind or passing wildlife. These adaptations were procedural rather than technical, reflecting the system's limited capacity for modification in the field. Countermeasures also included physical barriers. Records suggest that in certain areas, obstacles were placed in rivers to impede crossings. These range from submerged stakes to floating debris. Such measures posed a particular threat to inflatable craft. Operators reported increased puncture risk and difficulty maneuvering around obstacles at low speed. In some cases, crossings were aborted to avoid damage that could not be repaired covertly. Mechanical reliability under operational conditions was mixed. While the integrated design reduced vibration-related failures, it introduced maintenance challenges. Enclosed engines were harder to service, and overheating remained a concern during extended use. Documentation implies that strict operational limits were imposed. Short run times, mandatory cooling intervals, and pre-crossing checks that reduced the likelihood of failure but increased preparation time. Enemy awareness did not always translate into effective counteraction. Even when guards suspected crossings, the lack of clear evidence complicated response. Firing blindly into water was discouraged, and dispatching patrols required authorization. Period reports suggest that this hesitation was exploited, with operators relying on the system's low signature to create doubt rather than invisibility. Not all deployments were successful. There are indications of crossings compromised by environmental factors rather than detection. Sudden changes in current, unexpected debris, or operator error led to delays or abandonment. In at least one instance, documentation implies that a craft was lost due to material failure after repeated use, underscoring the system's limited durability. The psychological impact on operators was notable. Reduced noise lowered stress associated with immediate detection, but increased reliance on environmental judgment placed greater cognitive load on crews. Training emphasized patience and restraint, qualities that contrasted with earlier, more forceful crossing methods. Period accounts suggest that this shift in mindset was as important as the technical solution itself. From the enemy perspective, the system's use did not immediately prompt a clear understanding of the threat. Reports from border units often described uncertain disturbances or unidentified movement, lacking the specificity needed to drive systematic countermeasures. This ambiguity limited the enemy's ability to adapt quickly, but it also meant that the system's effectiveness depended on continued surprise. As operations continued, it became evident that the system was not a universal answer. Its value lay in specific contexts, under specific conditions, and against specific defensive practices. The balance between discretion and capability remained delicate. Any increase in power or speed risked reintroducing detectable signatures, while further reductions compromised operational viability. By the time broader assessments were conducted, the system had proven itself neither a failure nor a decisive breakthrough. It functioned as intended within its narrow parameters, shaping tactics and expectations on both sides of the river. Yet questions remained about its sustainability, adaptability, and long-term relevance as enemy awareness grew. These questions would become central to later evaluations, particularly as records were reviewed and the system's place within the broader landscape of wartime innovation was reconsidered. Assessing the long-term significance of the rubberized boat engine is complicated by gaps in the historical record. Documentation from the period is fragmentary, and much of what survives appears to be indirect. Test summaries, operational notes, and post-war recollections rather than complete design files. It is unclear how many units were produced, how widely they were distributed, or how consistently they were employed. In some cases, references to the system appear only once without follow-up, suggesting either limited use or deliberate omission. Several factors contributed to this uncertainty. Records indicate that small-scale clandestine equipment was often excluded from centralized archives. Designs were modified locally, components were reused, and unsuccessful trials were dismantled without formal reporting. In addition, post-war priorities favored documenting weapons and systems with clear battlefield impact. Quiet river crossing equipment did not fit neatly into these narratives and was therefore underrepresented. Technical limitations also constrained the system's longevity. The reliance on rubberized materials introduced aging issues. Period compounds degraded over time, especially when exposed to fuel, oil, and ultraviolet light. Documentation implies that storage conditions were critical and that improperly stored units lost elasticity or developed microcracks. These vulnerabilities reduced confidence in long-term stockpiling and favored short-term deployment. There were also operational trade-offs that limited broader adoption. The system required trained operators who understood its constraints. It was not forgiving of misuse. Excessive load, abrupt throttle changes, or prolonged operation could negate its advantages. In organizations accustomed to standardized equipment, this sensitivity reduced appeal. Records suggest that planners preferred tools that could be issued widely with minimal instruction, even if they were less discrete. From an engineering perspective, the system's influence appears to have been indirect rather than explicit. Later developments in low-signature propulsion and vibration isolation echo similar principles, but there is little evidence of direct lineage. Instead, the project seems to have contributed to a broader understanding that materials traditionally considered structural compromises could be leveraged for acoustic and mechanical advantage. This insight would resurface in other contexts, though not always with acknowledgement of its wartime origins. The psychological dimension of the system's use may have been its most enduring effect. By demonstrating that ambiguity could be as valuable as silence, it influenced how planners thought about detection and response. The goal was not invisibility, but uncertainty. This reframing of the problem, shifting from avoiding detection to delaying interpretation, appears in later doctrines, even if the specific technology did not persist. Enemy adaptation further limited the system's relevance over time. As guards adjusted their practices, the margin of advantage narrowed. Increased emphasis on visual surveillance, physical barriers, and random patrols reduced reliance on acoustic cues alone. Documentation implies that once this shift occurred, the system's benefits diminished, reinforcing its role as a situational rather than permanent solution. It is also possible that some records were intentionally destroyed. Covert equipment often carried political sensitivities, particularly when used in neutral or disputed territories. Post-war governments had incentives to minimize documentation of such activities. The absence of comprehensive files may reflect deliberate erasure rather than oversight. In evaluating why this solution mattered, it is important to consider what it represented rather than what it achieved numerically. It addressed a narrowly defined problem with a narrowly tailored response. It accepted limitations openly and traded performance for discretion. In doing so, it challenged assumptions about what constituted effective engineering in wartime contexts. The rubberized boat engine did not redefine river warfare, nor did it render borders obsolete. Its impact was measured in individual crossings, delayed reactions, and moments of uncertainty rather than decisive outcomes. Yet within those moments, it demonstrated that engineering solutions could shape enemy perception as much as physical reality. In the broader landscape of wartime innovation, the system occupies an ambiguous position. It was neither a prototype for mass adoption nor a dead-end experiment. Instead, it functioned as a proof of concept, that integrating material science, mechanical design, and human factors could yield solutions to problems that resisted conventional approaches. The incomplete nature of the surviving record mirrors the system's operational philosophy. Just as it sought to leave minimal trace on the water, it has left only a faint imprint on history. What remains is not a complete blueprint, but an example of how constraints, when taken seriously, can lead to unconventional and situationally effective designs.